Hello gentlemen, here's an example video on electrochemical cells, cell potential, and free energy, a combined problem. So here's your problem. A half cell containing zinc metal in a solution of zinc nitrate is wired to a half cell containing aluminum metal in a solution of aluminum acetate. A. Label the diagram below on the next slide, identifying the anode, cathode, and flow of electrons. B. Write the half reactions of each part of the cell. Write the overall redox reaction that occurs in the cell. C. Using the standard reduction potentials, calculate the E naught cell of the cell. D. Is this redox reaction spontaneous? Justify your answer by calculating G. Okay, to start off, so A, we're labeling the anode and the cathode and showing the flow of the electrons. Well, that's going to start here. So we have aluminum and zinc as our metals, those two there. According to my metal activity series here on the right, aluminum is more reactive than zinc, so aluminum is going to displace zinc in solution. So know that. The solid metal aluminum will displace zinc in solution. So we can choose whichever side over here to start with. Since we did this in class, I'll do the opposite. I'll make this aluminum metal there, and it said that aluminum metal was in a solution of aluminum, can't see that, aluminum acetate. So that's C2H3O2 1 minus down there. And if this is the aluminum, then that must mean over here is our zinc. And zinc was in a solution of zinc nitrate. Okay, so if aluminum is more reactive than zinc, then it will push electrons from itself over to this side. If that happens, that means aluminum is losing electrons, so we have oxidation happening here. We know the oxidation happens at the anode. So this side would be the anode. We have reduction happening here. That's happening at the cathode. That's T. Now, B says that we are to write the half reactions and the overall reactions. So for my half reactions, I'm going to write the oxidation reaction and the reduction reaction. So for oxidation happening at the anode, I'm starting with aluminum metal. It's a solid. It's going to be giving away its electrons to form Al 3+ in solution. I know 3+ because aluminum is going to form a 3+ charge in solution. That's aqueous. And it did that by giving away 3 electrons. My reduction, so this is oxidation, my reduction half reaction is going to happen from the cathode side, cathode half reaction. That's where I'm going to have my substance in solution receiving those electrons. So zinc 2+, which is an aqueous solution, receives the 3 electrons and produces solid zinc. And that's your reduction half reaction. Now, to write the overall reaction, this is incorrect here. Zinc is going to receive 2 electrons because it can't receive 3 electrons and go to zinc solid. It can only receive 2 electrons. So now I have an imbalance in my electrons here. Since I wasn't given any information about acidic or basic solution, I simply do a very simplified balancing or writing the overall reaction here. To write the overall reaction, I find a common multiple between my number of electrons here, which is going to be 6. So I multiply this half reaction by 2 and this half reaction by 3, giving me a different total of electrons. And if I were to add all that up, I would get 2Al. Well, not added up yet, just yet. And 2Al3 plus 6 electrons. And for my other, I get 3 zinc 2 plus aqueous plus 6 electrons going to 3 solid zinc. My electrons cancel, and now I would simplify and add these two up. Now I can do that, and I will do that right up here. So in my reactant side, I have 2Al plus 3Zn 2 plus, and that's aqueous, going to 2Al3 plus aqueous plus my 3 solid zincs. This would be my overall reaction. It's not specified whether acidic or basic, so all I really do is balance my electrons and combine the two half reactions. Now, letter C, calculate the electrochemical cell potential. So we have silver and zinc. So zinc is here. Sorry, aluminum and zinc, and aluminum is there. So my equation is here below. So we take the potential of the cathode, subtract from that the standard reduction potential of the anode. So my cathode, these are all reduction half reactions, so they're already in the format that we want them at. So at the cathode, we had zinc. Zinc was receiving those electrons. So for zinc, we have negative 0.76 minus, for aluminum, negative 1.66. So again, we just keep them as is. We do not flip them if they're given to us in this format. And you have to check that you have a positive answer when you do this, and of course we do. We get 0.90 volts. And for letter D, you're calculating if this reaction is spontaneous or not by calculating delta G. Now our equation that governs this is delta G equals minus NFE, and F is given here above. So to calculate this, we have to think about how many electrons were transferred in our overall redox reaction. We wrote the overall redox reaction, we balanced it, and it was 6 total electrons, which is going to stand for 6 moles of electrons here. So multiply that times Faraday's constant, which is 98,485 joules per volts, times moles, or per mole. And then we tack on that our cell potential was 0.90 volts. And from this we get .32 times 10 to the 5th joules per mole. And sorry, it's negative 5.32 times 10 to the 5th. So since we do have this negative value, Delta G is spontaneous. Alright, gents, please review this and use this for your studying.